You get the right one here. No, gonna do this one. Okay, so we're gonna do the Lab2Theory video now. So last time we said that Aristotle developed his logic around 300 BC. Okay, now what happened afterwards was in the 1800s, George Boole put Aristotle's logic in an algebraic framework. He introduced variable names such as x and y, and operators such as plus and dot, and he had constants, Boolean constants 0 and 1. All right, then around the 1930s, Claude Shannon, a graduate of the University of Michigan and MIT, applied Boole's algebra to switching circuits. Okay, so now this, remember that we said we could represent switching circuits with switch contacts. So here we have switch contact, x represents x. If it's open like this, x equals 0. If it's closed like down here, it's x equals 1. And we can use normally open and normally closed contacts in opposite states. Okay, so what happens here is if A closes, B opens, and vice versa. That gives us the ability of representing complements in these switch contact diagrams. Now here's a skill you need to learn, which is given a Boolean expression, draw the gates for it, and vice versa. So work with 2-1, A, B primed, or C. Okay, we need a NOT gate to prime to B, AND gate to AND it with A. Now, write the partial result on your diagram so you don't get confused. Then you get A, B primed. That needs to be ordered with C, which we use the OR gate for, and get A, B primed, or C. Now, working backwards, we've given this. We see that you get A, and it would B primed, right? A, B primed there. Then we see it gets ordered with C, right? A, B primed, or C, and then you can write your expression there. Now, the next one, 2-2, looks more complicated, but the trick is to start in the innermost parentheses, C or D. So generate C or D first with the OR gate, then AND it with an A with an AND gate, then complement the whole thing, then OR it with B AND it with E. And of course, you can work backwards with this one. Now, where are we? Okay, so now what's going on? Okay, so we said that given an operator, we could represent, like AND OR, we could represent it in a truth table. Well, it turns out it can also represent a Boolean expression or a Boolean function with a truth table, as we see done here. Okay, so we know there's 2 input variables, therefore 4 rows. And for convenience, we generate a helper column called A primed, because we want to generate a table for A prime B. Then we work between these 2 columns, A primed and B, to get A primed or B, okay? So 0 or 1 is 1, 1, or 1 is 1, 0 or 0 is 0, 1 or 0 is 1. Okay, so we can see how we can get a truth table for a Boolean function. Now, knowing this, we can prove with a truth table that 2 Boolean expressions are equal. And also, they can be said to be equivalent. You can say either equivalent or equal. Doesn't matter. So 2 Boolean expressions are said to be equal if they have the same value for every possible combination of the input variables. Okay, we're going to prove this with truth table. So here's the 2 expressions to the left and right of the equal sign. Left side expression, we're going to tabulate that. Okay, and we'll use the helper column B with A, those 2 columns. And we'll generate AB primed, right? By ANDing 0 and 1, 0 and 1, and so forth, right? Now, once we've got AB primed, we need to OR that with C. So we OR between these 2 columns, the AB primed and the C column, and get the AB primed or C column. So now we've got the left side tabulated right under here. Okay, now right side, you need to tabulate A or C, which is not much of a problem, work between these 2 columns. Tabulate B or C, work between those 2 columns, and then AND them together here. Now you see that this column of information and this column of information are exactly the same. So the 2 expressions are equal. Okay, now we can prove things also algebraically, all right? So we can start off with basic theorems. Now, operations with 0 and 1. X or 0 is x, and x or 1 is 1. Okay, now, what's on the right here is a dual. Every equation or expression has a dual. You form the dual by changing the plus to the dot or vice versa, and changing the 0 to a 1 or 1 to 0 or vice versa. Okay, and then you get the dual. So, something interesting. Whenever an equation is true, its dual is also true. Okay. Now, idempotent, x or x equals x, or you can work from right to left. Okay, you can add in an extra x or remove it. Okay, involution, double complement something, you get the original back. Complementarity, x or x prime equals 1, x and x prime equals 0. Now here, we can illustrate the x dot x prime equals 0 with relay contacts. Okay, and so we have a dot a prime equals 0. Okay, so a is closed and a prime opens and vice versa, so it's equivalent to an open circuit always. Now, we have the commutative associative laws just like we had in ordinary algebra. So x, y is the same as yx, x or y is the same as y or x. Now, with three variables, it doesn't matter which two you end first or which two you or first. So we can speak unambiguously about x, y, z, or x or y or z without brackets. Now, because of that, we can talk about a three-input AND gate. F equals ABC. And here we have a tabulation for the three-input AND gate using AB as a helper column. Now, of course, we always also have distributive laws. Okay, x and y or z equals x, y, or xz. X, y, or xz. Now, because of duality, we have a second distributive law. X or y, z is x or y, x or z. And of course, we can work from right to left if we need to. Now, De Morgan's law, we want to find the complement of a bracketed expression. We can move the complement inside. Okay, so you change each operator to its opposite. Plus goes to dot and vice versa. Okay, but then the variables inside get complemented and the brackets can be removed. Okay, now you're probably saying is, hey, I thought that was a dual. No, this is similar to the dual because plus goes to dot and vice versa. 0 goes to 1 and vice versa. But in the complementing, you complement the variables inside, which doesn't happen with the dual. Okay? Now, x, y, whole thing primed is x primed or y primed. You can also work from right to left to move the complements outside the brackets. And you can prove these De Morgan's laws with truth table proof. Okay, now back to truth table proofs. Forgot to say this. Why is this so important? Because our lab hinges on this today. We are going to prove that a unsimplified Boolean function f equals a simplified Boolean function g by the truth table method with the waveforms representing the truth table. Okay, so to recapitulate, we have all these operations, okay? Idempotent, involution, complementary, and so forth. Now, those theorems are actually adequate, but they're not efficient. So you can solve any problem with laws alone, basic laws alone, but it's convenient to introduce simplification theorems because they make things more convenient. Okay, so we have uniting theorem. You have x with y primed. The y primed is redundant. You can get just x. And a similar thing happens with the dual. Now, absorption, x or xy is x. Elimination, x or x prime, y is x or y. You eliminate one literal. What is a literal? literal is the occurrence of a variable or its complement. Now here we have duality. You form the dual of this product expression here, x or y or z. Okay, so the pluses become dots or ands, and you get x, y, z. Similar thing happens with a dual. And you have this term for multiplying out or factoring. So you could actually do this the long way with distributive law and prove that this side equals this side. Now, consensus theorem. You can eliminate a redundant term. You find something in x and something in x primed. Then x becomes with a y. The x prime comes with a z. So the yz is redundant, can be removed. A similar thing happens with the dual. Now, all these things are provable in terms of the basic laws. So that's why they save lines in your proof. Okay? So what about this? xy or xy prime. Factor out the x. The y or y prime equals 1. You get x. What about this one? Well, x is the same as x dot 1. And it's ordered with xy. Now factor out the x. 1 or y is 1. So we have x and 1 with x and so forth. Okay? Now, let's work on finding a complement. Okay, so you have an expression to complement this. So, looking inside here, I would work between the bracket expression and the c prime first. Put in a plus here, and I have to complement what's to the left and what's to the right. Okay, so now, if I complement what's inside the brackets here, I get ab primed, and then cc prime to c, it comes out to ab prime to c. This one may be more complicated, I don't know. So we're going to work between the or and the e first. Okay? And so the plus becomes an and everything to the left gets complemented, everything to the right gets complemented. Okay, so we have to introduce square brackets here. Okay, so inside the square brackets, we have to keep on going. So this and becomes a plus. Complement to the left and complement to the right, dd primed. D primed is d. You complement this, you get ab primed. Yeah, okay, then you have to complement this yet. Next, okay? So you get plus becomes dot, you get a prime, b primed, and c primed, or d. The whole thing with e primed. Okay, now, see this ab primed? You got to get that primed from outside the brackets to inside. So the and becomes an or. A gets primed, the b gets primed again, and so a prime becomes b. Now, the Morgan's law can be extended to n variables. So you can see, for example, n equals 3. So you have the 3 x's with the, okay, complemented, okay. So it is the same as, okay, it ends up being the pluses go to n's, and you get x1 primed, x2 primed, x3 primed. Okay, so complement of the product is the sum of the complements. Complement of the sum is the product of the complements. Now, consensus theorem. Let's look at this again. You get x with y, x prime with z, so the yz is redundant, gets removed, and then you have this. Now, the term that's eliminated is called the consensus term. Okay, so you can form the consensus term here. See, I saw the x with the y and x prime with the z. Form the consensus term yz. Recognize it here and knew it was redundant. And the consensus has, of course, a dual. The consensus theorem has a dual. Now, we're going to look at the different ways of simplifying expressions. We can do combining terms, eliminating literals. So for combining terms, can use the uniting theorem. Xy or xy prime equals x. Now, we're going to use x's and y's and z's in our theorems as metavariables to represent expressions in the problem variables, a, b, c, d. Okay? So in this one, x is a, b, d prime, and y is c. So we see something with c prime, something with c. Okay? you see, in each case, ABD prime, but once with C prime, went with C. So you can eliminate the CC prime, get ABD prime. Okay, now here we're going to use the ability to duplicate terms, to duplicate a term and use it more than once for elimination. Okay, so we duplicated ABC. This ABC uses uniting with this term. This ABC uses uniting with this term, and we get a major simplification. Okay, now, eliminating terms can be done by absorption theorem, x or xy equals x. So here we have got A prime B by itself. Now we got AB prime and with something else C. So the C is redundant, gets eliminated. So again, the substitution is x equals A prime B. Now this one can do by consensus again, CC primed. The consensus term is AB prime D, which is this one gets eliminated. And you have this. To eliminate literals, use the theorem x or x prime y equals x or y. Eliminate that literal, x prime. Did I tell you what a literal was? A literal is the occurrence of a variable or its complement. This eliminates one literal. Example. I'm going to use this successively to reduce this expression. So first factorial A prime. What do you see? B or B prime CD. Now, by what's it called again? All right. All right, it doesn't matter. Okay. So what's that theorem called again? So the names changed from the 4th edition textbook, which we used to use. So yeah, you have uniting theorem and absorption. Yeah, it's called elimination theorem. Yeah, you do elimination with elimination theorem. Okay, elimination theorem. Okay, so we're going to use elimination theorem successively to reduce this. All right. So you've got the A prime factored out. So you got B or B prime CD. So it's of the form X or X primed Y. So this literal B prime goes away. Get this. B or C prime D prime. Now, this is not shown here, but this A prime got multiplied back through. And then we took the B out. Okay? And we've got B and A primed or A C D primed. Okay, this is the form X or X prime Y. Okay, with this A being the complement of this A primed. That A literal gets removed. And get A primed or CD primed here. Now multiply back through and you've got the answer. All right, so we have done what? Combining terms, eliminating literals. So the combining terms was done by uniting. We used to call the uniting something else. Okay, now it's called uniting. And then we have the uniting, then we have the absorption, and then we have the elimination. All right. Yeah, we used to call the uniting, it used to be called adjacency. In the 4th edition textbook, we called this adjacency. Now it's called uniting. Okay, so that is really, really, really good. Okay, so we got over the theory. And now we can work on your lab. We can actually do this now. So here's your lab you have to do. Okay, so you're given this complicated expression. Okay, you're supposed to produce an equation G for the simplified version. All right? And yeah, it's supposed to prove F equals G by the truth table truth table method with the waveforms representing the truth table. Okay? So, yeah, well, how does that prove it? Well, we said in the truth table method, the F and the G have the same value for the same input variables. Okay? Going row by row. So going row by row in the waveforms is equivalent going by time slot by time slot. So in every time slot, you have the input variable set to certain values. And then the f and the g will be the same for those values in every case. And that proves that they're equivalent. Okay, so let's work on this. Oh yeah, in your report. Okay, the simplification procedure, you need to type or scan it in. You need a screen capture. You're going to have actually one BDF diagram. You need a screen capture of that in your wave report. Okay, and you need your waveform results and explain what the waveforms represent, what do they prove. All right, and of course you need some other things, okay, to have a complete report built around these things. You need the theory section, procedure section, and so forth, right? Okay, so let's get to work on this. Okay, you probably don't have a lot of experience with simplifying something like this, so I guess we work on it together. All right? Okay, so Control C. Okay, go down here. Control V. Okay. Now, can I make it bigger? Yeah, well, maybe go to 16. I don't know. Yeah, it's better. Okay, so we look at this. Now, what's good about this is the A's are already factored out. We would have to do that if it wouldn't be already done. Okay, so first thing I see here is BCD or CD. What's that? Well, you're not here right now to answer, so I'll tell you. It's what they call an absorption. So you got CD by itself, then CD with something else. So reduce this to CD. Control C. Control V. All right, so just have CD. All right, now what? Here. Let's look at this. What's going on here? Oh yeah, something with D, something with D prime. So I got the C with the D and the B with the D prime. So the BC is redundant, gets eliminated. Okay, Control V. Good. Now, what did I say I was going to do? Eliminate the BC. Now, there's another consensus over here based on the D and the D primed. So the consensus term is AC. This gets eliminated. Okay. Now what? I said what was eliminated. Consensus term was what? AC. Okay, now what? Well, let's just use distributive law, multiply through. Okay, take out some brackets. Okay, so ACD. Okay, and we said we have to do distributive law. So that would give us AB D primed and ACD. Okay, again, distributive law here. Get A prime C D primed. Or A primed AD. Well, okay. A primed AD. Now, whenever you get A primed, that's 0. And 0 ended with anything is 0. So, oh yeah, we'll get rid of that bracketing. Control C, Control B. Okay, we said we're going to get rid of this, right? Well, okay. Now what? Well, I see I got ACD, ACD. And I really don't need it. So Control C, Control V. Could eliminate the extra ACD. Okay. Now, I see ACD, A prime, almost, right? If this would be a CD, I would have ACD and A prime CD. I could say CD or ABD primed. So I'm looking for a way to simplify this further. Now, that's going to be it. So it simplifies to that. Maybe I'll save this for further reference in case I need it. No, just forget it. Okay, so I guess that concludes this theory lecture.